welcome to our new video. Today we will do some exercise questions that are related to our previous chapters. So first of all, let's look at the first example. We have x minus y, 2x plus 3y. So this is a simple system of two unknowns and two equations. So actually we have seen the Gaussian elimination method, but we can also use the simple algebra to solve such systems. And then we can also apply the Gaussian elimination method, and we can actually verify that what we obtain from the Gaussian elimination method is also correct. So it can help you. So you can basically do some operations in the first equation. For example, if we multiply the first equation by minus 2, so we get minus 2x plus 2y equals to minus 14. So if we add these two equations now together, these minus 2x and plus 2x, they cancel each other. And then you get 5 times y equals to minus 20. So you get y equals to minus 4. And then if you plug in the y value in one of these equations, you can solve for the other variable x. So then you can see that 7 minus 4, that gives you x equals to 3. Now similarly, one more example, 2x plus y equals to 2, x minus 3y equals to 15. So in such problems, if you are trying to solve it with simple algebra, then you can basically multiply, for example, the first equation by 3. So this becomes 6x plus 3y equals to 6. And this time I have already minus 3y, so if I add these equations side by side like this, these terms cancel each other, and we get 7x equals to 21 and x equals to 3. And then just by plugging in the x value in one of these equations, for example here, if you plug in x equals to 3, that means minus 3y equals to 12 and y equals to minus 4. So we get the solution. Now another example, here I'm given a 3 by 3 system. So this one is a bit, a larger, slightly larger system than the previous examples. And you can first write our matrix of coefficients and the right hand side of the equations. So the coefficient matrix is given here, 1, 2, 1. I mean, you just write these coefficients and then write down the right hand side of these equations. And as we know from this Gaussian elimination method, what we are doing here is some row operations in order to get zeros in the below the diagonal terms. So if we have a diagonal here on this line, below the diagonal we want to get zeros so that we can obtain the third variable x3 directly, because we want to get x3 directly from the last equation in the third row. And in order to have that, we do some row operations. And also notice that if we start with 1 in this first row, that will simplify our job, because we can, for example, multiply the first equation by minus 2 and then add to the last row. Or you can multiply the first equation by minus 3 and then add to the second row. These calculations, as you see here, are simplified if we have 1 as the first term here in the first row. So, for example, if we multiply with minus 1 and add to the third row, that gives us 0 here. And then 7 minus 4, we get 3. And then 9 minus 2, we get 7. And we have 23 minus 8. That gives us 15. And then now you can try to cancel another non-zero term, which is 3. So you multiply with minus 3, the first row, and then add to the second one. So that gives you 0 as you wish. And then you have 8. So we have this 8 minus 6, which is 2. It's given here. And then 7 minus 3, we have 4. So this is 2, 4, and 8 here. So basically this simplifies because now 2, 4, and 8, we can divide each term by 2. So that gives you 1, 2, and 4. Okay. Now, if you multiply the second row by minus 3 and then add to the third row, this term here will cancel and become 0. So we get 0, 0, and then 7 minus 6 we get 1, and 15 minus 12 we get 3. And this implies 1 times x3 equals to 3, so that means the x3 equals to 3. And then the rest you just plug in back to your previous equations and solve for x2 and then solve for x1. So using this, x3, you can plug in back to our first equation. So we have x1 plus 2. Sorry, we use this second row here. So I forgot. So we have x2 plus 2 times x3 equals to 4. And we already obtained x3. So if we plug in here, we can see that x2 equals to minus 2. And then going to the first row here, that means x1 plus 2 times x2 plus 1 times x3 equals to 4. So the right hand side equals to 4, and then you can finally obtain the one remaining variable x1 as equals to 5. Let's look at another example quickly. Again, you have a system of equations, and we have the unknown variables x1, x2, and x3. So as usual, if we are doing Gaussian elimination method, we should write down these coefficients and then write down the right hand side of this system. So we write it down here, and then we start to do our row operations in order to simplify this system. So as usual, actually we would prefer to have this 1 in the first row because, as we mentioned already, we can multiply the first row with some constant and then add to other rows. This will help us to eliminate some non-zero terms here. For example, if we have this 1, 1, 1 as our first row, this is our first row, and then we are allowed to do this kind of swap. So basically we have now if we basically multiply the first row with minus 2 and add to the second one, because the second row is 2, 1, and minus 3. So if I multiply the first row by minus 2 and then add to the second one, this will become 0, minus 1, and minus 5, and we have minus 6. So that's our new updated second row. And we can actually also multiply the first row by minus 5 and then add to the last row here. So that will eliminate this term here. So it becomes 0. This becomes 6 minus 5. That's minus 1. So we get this 0 here after multiples, and then we have 1 here. And then 8 minus 5, we get 3 here. Okay, so these terms. And then 8 minus 5 again, we get 3 here. Now, in order to we want to get rid of this guy as well, so we add now the second row to the third row. This becomes 0, and this becomes minus 2, and here minus 3. So as a result of this Gaussian elimination, we simplified as we wanted. And using the third equation here, this means minus 2 times x3, sorry, this is minus 2 times x3 from the last row here. That's the meaning of this. That's equal to minus 3. Or in other words, x3 equals to 3 over 2. So we can see the details of this calculation here. x3 equals to 3 over 2. And then once we obtained x3, then we just go back recursively. Notice this is minus x2 minus 5 times x3 equals to minus 6. So once we plug in x3 in this equation, that gives us x2. And then finally, using the first equation as x1 plus x2 plus x3 equals to 1, basically we can solve the value for x1. And that completes all the unknown variables in this example. Another question here. This time you want to analyze the solution with respect to potential values of k. And if we look at the problem x plus 3y and 2xky equals to 0, we can notice that actually these two equations seems to be very similar. And if we multiply the first equation by 2, that gives us also 2x and 2x here. So this is 6 times y, k times y. So both of these equations, they have the 2x common. So if the second term is also the same, then basically we will have effectively one equation and two unknown variables, and that will yield infinitely many solutions for this system. So if k is not equal to 0, then this will yield a contradiction if and only potential solution will be the trivial solution. That means x and k are both equal to 0. Otherwise, these two equations cannot be satisfied at the same time. So that will be the only solution here will be the trivial solution for k is not equal to 6. Another example, this time we have a system of actually two equations but four unknowns, x1, x2, x3, and x4, given in this format. And we can write the Gaussian matrix. And in this example, the second row here implies actually x2 plus 2 times x3 minus 7 times x4 equals to 0. And as you notice in this equation, we have actually less equations than the number of unknowns. And in order to write the solution for this type of problems, we need to do some parameterization. And the parameterization is done with respect to x3 and x4. So by setting these parameters to be defined, then we can write the rest of the variables as usual. Okay, another example. Now we are trying to find and calculate this determinant. But these determinants, remember, we can do some row operations. That doesn't change the result of the determinant. So if the result of the determinant is not changing, we can do such row operations and then simplify our expression and then finally calculate the determinant. Okay. Usually we don't prefer to directly apply our determinant calculation methodology to these type of problems because this will be a bit more work for us in terms of calculating the determinant one by one. But instead of approaching this problem, we can do some row operations and then perhaps reduce our matrix into a diagonal form. And if it is in diagonal form, the calculation of the determinant will be simply the product of these diagonal elements. So the diagonal products can be easily calculated. And in this example, we have 2 minus 1 and 2. So basically you can add the first row to the second one. This becomes 0, 0, and 6. Or you can multiply the first row by -2 and then add to the third row. So that becomes 0, 0, and then 5. So basically, now as you see, this is simplified because we have below the diagonal terms are equal to 0. So this simplifies our determinant calculation. However, as you see, the diagonal terms, we have a 0 term. So that means the determinant of this expression is going to be just 0. Another example, suppose you are given an unknown variable x, and we have this x dependent notation. We have the determinant of this matrix, but the elements of this matrix are given as x, and x is the same as you see in many rows and columns of this matrix. So we know that we can factor out some common terms. So this becomes 1, 1, 1. So we write x squared here. And then we can also take out these expressions under the common parentheses like x. So if we put this under x parentheses, this is 1, 1, 0. This is 1, 1, 0. Alternatively, that's 1, 0, 1. So once we put this, now it's becoming simpler. Now we can interchange the location of the second row with the third one. So that becomes, we have 0, 0, minus 1. Actually, you can, for example, subtract the first row from the second one. So that gives you 0, 0, minus 1. And then you can subtract the first row from the last one. That gives you 0, minus 1, and 0 here. Now, the calculation of this determinant becomes easier. So if we now swap these two columns with each other, so we get 1, 1, 1, 0, minus 1, 0, 0, 0, minus 1. So basically, if we multiply the diagonal terms, this gives us x cubed minus 1 times minus 1, that's plus 1. So the final result we get is x cubed. Another example, it's asking us if the inverse exists for the below given matrix. And in order for the inverse to be well defined, we need the determinant of the matrix to be non-zero. And suppose you are given this problem here, A, you have 1x minus 1, 1 minus 2x, 0, 0, 1. So how do we check the determinant of this problem? Actually, we write the determinant and then we can do some row operations as needed to simplify the calculation of the determinant. So since we are given this, we can subtract the first equation from the second one. Actually, that simplifies the expression here. So that becomes 0, minus 2, minus x, and then you have x plus 1. And then the third row, that's 0, 0, 1. Now, as you see, all the below the diagonal terms are 0. So we have obtained a nice form here. And we can easily check, take the determinants. That is going to be 1 times minus 2 minus x times 1. So the condition is that for the inverse to be well defined, this should not be equal to 0, and that implies x should not be equal to minus 2 for the inverse to exist. Another example, here we have A equals to 3 by 3 matrix, and you are given B inverse times B transpose equals to A times B. Now the question is, what's the determinant of 2 times B? Notice that we can apply the determinant to both sides of this original equation. That gives us determinant B inverse times B transpose. But same thing as B inverse times determinant of B, because the determinant of B transpose is same as itself. And we can reduce that as furthermore, this is 1 over determinant of B times determinant of B, which is equal to 1. So finally, to complete this, what we were looking was determinant of 2 times B. And we have already obtained determinant of A times determinant of B equals to 1. And then we can say we can see that here determinant of B equals to 1 over determinant of A, and we already calculated that this determinant is equal to 4 because of the this is the upper diagonal matrix now, and below the diagonal terms are just 0. So we can calculate the determinant as the multiplication of the diagonal terms. 2 times 1 times 2, that's the determinant of A, which is in this case equal to 4. So the determinant of 2 times B equals to 2 to the third power times determinant B, because we have a 3 by 3 matrix. So we can actually, in this case, actually each element of B is multiplied by 2, and this is 3 by 3. Therefore, basically this is 2 to the power 3 times determinant of B. And that's given as 8 times 1 over 4, that equals to 2. Now another example, let's look at this quickly. Here you are asked to use the Cramer's rule to solve this system of equations. You are given a system. You will start to write that as your matrix A, a matrix of coefficients, and then as you see, we have these coefficients, and we will do some row operations to simplify this. So add the first one to the last one. That's 0, 5, and 0. And then you can multiply the first one by minus 3 and add to the second row here. So this will also cancel out. So that's going to be minus 1, minus 6, minus 7, and 2 minus 3, that's minus 1, and then we have 0, 5, and 0. Okay, so by doing one more row operation, actually we can also get rid of this term and make it equal to 0. And the last term remains the same because we have 0 times anything is still 0, and then adding or subtracting from minus 1 is not going to change any result here because of this 0. So the determinant of this expression is 1 times 5 times minus 1 because they are on the diagonal. And off the diagonal terms below this diagonal are 0 anyway. So this gives you the determinant of A. And next, you need to solve for x1, x2, and x3 respectively. And you can see that the determinant of A is already calculated here. And now we are just dividing by the determinant of A. Sorry, but here actually for each unknown variable, we are replacing the first, second, and third rows with the right-hand side values of the equation. So the right-hand side values of this equation are given as, for this problem here, we have 1, 4, 1. So this 1, 4, 1 is put in the first x1. This is replaced for the first column. In the second case, this is replaced actually for the second here, second column, and then the third column. And the other terms are the same as the original coefficients. But the denominator here is always the same. minus 5 minus 5. And that gives us, if we do these calculations, and that gives us 16.5 and 2 over 5 as x2 and x3, sorry, x1 and x2 values, and then x3 equals to minus 19 over 5. Another problem, again the determinant, and you are asked to solve for x given this problem. Remember, this is below the diagonals are 0. So that means I can multiply the diagonal terms to calculate this determinant, because below the diagonal terms are 0. And if we multiply the diagonal terms, we have x times x squared, that times 1 minus x equals to 0. And from here, this can only be satisfied at x equals to 1 or x equals to 0. Another example, here dy dx equals to minus 3 times x squared y, and we want to solve this. And first of all, notice that we can separate this first order equation. So dy term can be combined by y, and then the x terms combined with the other x terms here. So we obtain dy over y, because we both divide both sides by, or multiply them by 1 over y. So y over y, that cancels. So we get ln of y equals to minus x cubed plus c, and ln y minus ln c equals to minus x cubed. And then the rest is what we already did before. So we take this transformation to the left side as ln of c, and then write this as ln y over c. And that gives us, if we take the exponential power of both sides, this becomes y over c equals to e to the power minus x. And finally, remember, this is initial value problem. So we will plug in x equals to 0, and that gives us c equals to 3. So finally, combining all of this together, we can write the special solution for this problem. Now let's look at a few more questions. One more problem. dy dx minus y equals to e to the power minus x. Again, you are given some initial value. So this looks like the integration factor method can be applied here, because I have some equation similar to this form here. Y prime, which is this one, this is y prime, plus some function of x times y, and the right side is q of x, another function of x. And indeed, this equation is in this form. So this is y prime minus y equals to e to the power minus x. And for these type of problems, integration factor method that we have seen can be applied. So you simply need to set what is your p of x, q of x, and the integration factor is mu of x. This one is simple integration factor, because you already, this e to the power px dx, this gives us the integration factor. In other words, if we multiply both sides of the equation with this mu, the left side becomes the derivative of the product. So as you see, if we multiply both sides by e to the power minus x, that is the integration factor, and the left side becomes the derivative of the product, okay? And the right hand side, we have the e to the power minus 2x dx. So essentially, the integral of both sides, we get e to the power minus xy equals to the integral of this expression, you know how to calculate, minus 1/2 e to the power minus 2x plus c. And finally, just write this solution for y of x, and then make sure we can satisfy the initial condition. So if x equals to 0, this will become minus 1 over 2 plus c, that's equals to 2 given. So given this initial condition, we can write the special condition, special solution as with this equation. After we substitute back this c, basically this is our special solution. Another example, you have dy dx plus 1 over xy equals to 5. Again, we are given some initial value. You can immediately think about the integration factor model, because I have y prime plus a function of x times y equals to another function of x. So here q of x equals to just 5, and p of x equals to 1 over x, which is the coefficient here. So apply the integration factor idea as usual, integrate both sides. So that gives us e to the power ln x, actually which is equal to just x. So our integration factor is just x. Multiply both sides with this x, so you get x times y prime plus x over x times y equals to 5 times x. And then integrate both sides, and that gives us x times y equals to 5x squared over 2 plus c, right? Because we know how to integrate this type of polynomials. And then finally, we can use our initial condition, which is given as y of 0 equals to 2. Yes, so basically we can just integrate both sides, so we get xy equals to 5x squared over 2 plus c. And then if you plug in the initial condition, you can solve for c. So that gives you the solution. As you see, you get 5x squared over 2 minus 3 over 2. Okay, another example. As usual, again, we have a first order, but as you see, this is nonlinear differential equation. So we need to do a substitution here, because we need to actually get this in a simpler form. We cannot directly apply integration factor, and it is not separable differential equation as well. But we have seen the substitution method. So if we let this term to be our v, that's our new variable, then this becomes y equals to v minus x minus 1. But notice that, what is dy dx? From this equation, if we go to the next one, dy dx equals to dv dx minus the derivative of this, x is just 1. So dv over dx equals to dy over dx plus 1. And then basically, if we do this, if we write this as dv dx minus 1, that's our dy dx, but this is equal to v squared. So that's our v squared on the right hand side. So you can write this as dv dx equals to v squared plus 1 here. Now this looks a bit more familiar, because now we can separate v terms from the x terms and get this dv over v squared plus 1, and on the other side we have dx. Now we are getting close. Basically, this is the integral of this expression is the inverse tangent of v, and on the right side we have x plus the integration constant c. So by taking the tangent of both sides, you can get v equals to tangent of x plus c. And then finally, we substitute v back to our initial equation here, and then you have minus x minus 1. Now this is our solution. Okay, one more question. Suppose you want to check if uh, basically if this differential equation is exact or not. Remember, what was the exact differential equation? So we have some function of x and y in front of dx, and we have another function of x and y. We will call this as n. So this is our m. So remember, now we have written this m, xy, and n of xy. So the exact differential equation should satisfy this property here. The y derivative of this expression, that is 2x uh, uh, yes, y derivative of this function m, 2x minus 2 times y, that is given here. And then on the other side, we have the n. Here we should take the derivative with respect to x. So we get 3x squared plus 2x plus 1 minus y squared. So we can notice that these two expressions are not equal to each other, and therefore this differential equation is not exact. Okay, so it is just asking us to check the exact whether this differential equation is exact or not. But if it is exact, we also know how to solve such differential equations, and if you want, you can also review this part as well. So we have just covered some more examples actually, but you should still go over our lecture notes and all the examples that we have seen in these lecture notes. So thank you for watching.